So let's take a look at some examples. Let's say we have, first of all, let's take a look at that plate of charge that was mentioned earlier. If you just got some wall and it's got a whole bunch of charge on it, let's say it's just got positive charge evenly distributed throughout the whole thing. And let's assume this is a very large wall, so large that we can treat it as effectively infinite in size. And of course, it's not going to be truly infinite, but let's say it's large enough and or we're close enough to it that we can treat it as being almost infinite in size. And we want to find the electric field if we treat this wall of charge as the source charge. With positive charge evenly distributed all over it. And we want to find the electric field at some location, let's say here, near the center, but out a little ways. If we want to find the electric field here, typically if you've got some object that's not just a point charge, you want to imagine it split into individual pieces of charge. Because you could imagine this very large plate as if it's a bunch of little tiny pieces. Each one of those tiny pieces can be treated as a point charge. So let's say we look at just this tiny point charge in the center. That's going to create electric field in which direction?
Will be away?
Yeah, a positive source is going to create electric field away. In the case of the center, the exact center charge is going to create electric field directly to the right. If we take a look at the one a little bit below, that's going to create electric field, again, directly away. So that's going to be up and to the right. And a little bit weaker because it's a little bit further away. But also, if we take a look at the one directly above the same distance, this one's going to create electric field down and to the right. And by symmetry, we should expect those to be the same. Likewise, if we go a little further down, this one's going to create electric field a little bit more up and a little bit less to the right, and a little bit weaker because it's a little bit further away. Likewise, that same distance above is going to create electric field down and to the left, down and to the right. So we can think of these contributions in pairs. Each point below the center creates electric field in some direction, but is matched with a point above on the other side, which creates electric field in a similar but opposite direction. And how do we find the total electric field if we've got all these little contributions? What would we do with those? Yeah, we can just add those together. And if we're adding those as vectors, if we think of these in terms of these pairs, like let's say this one and this one. If we're adding this vector plus this vector, what's going to happen when we add those pairs?
Cancel out.
They partially cancel out. They're not going to completely cancel out, but what parts of them do cancel out?
The vertical component?
Yeah, if you split this into horizontal components and vertical components, the horizontal components, the x components, are both in the positive direction. But the vertical components, we've got a positive vertical component and a negative vertical component. So the upwards and downwards components cancel out. But the rightwards and rightwards components combine. So when we add those, we should expect a large vector to the right from adding those together. You could also look at this geometrically if you're adding these vectors head to tail. Going this much up into the right direction plus this much in the down and to the right direction equals this total here. So they still add up to a vector to the right. And that's going to be true for any such pairing. If we combine the contribution from this piece plus the contribution from this piece. Those also, we've got up and to the right, down and to the right. The up and down components cancel out, the right and right components combine. So these are still going to add up to a vector just to the right. In fact, if we assume we've got a point at or at least near the center, all the upwards and downwards components cancel out because all these can come in pairs. They can be categorized into these pairs, a piece above the center and a piece below the center. And so we end up with all the upwards and downwards components canceling out. All we have left is to the right. So the total electric field at this location should just be a vector straight to the right. Any questions on that so far?
I have a question. Mm-hmm. So I don't really understand how you're getting the initial, like for each one, you're getting one arrow going kind of up and the other one going kind of down. I don't understand how you're getting those. These
individual contributions are from individual little pieces of charge. So if we have, for example, if we're looking at, let's say, just this piece creates electric field here in a direction directly away from it because it's a positive source. So that's one contribution to the electric field. But also, if you take a look at the point exactly opposite that, like same distance above the center, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, this piece creates electric field at that point, or at least a contribution to the electric field away from itself. So that's going to be down and to the right. And if we pick a point directly above a certain distance and directly below the center, the same distance, then we should expect symmetry here. We should expect these to be the same amount of electric field, but exactly reflected across the central axis. So the upwards and downwards components cancel out. The rightwards and rightwards components combine. So these two electric field components combined together create just a purely to the right electric field.
So how do we know that the electric field is going to be pointing away?
Anytime you've got a positive source charge, electric field is always going to be pointing directly away from a positive source charge. At least the contribution from that piece of charge. So this little bit of positive charge, if we ignore everything else and look at just this as the entire source, that source charge creates electric field pointing straight away from itself.
Okay, so so is that particle, like the dot, is that like a negative or a positive?
This one here?
Yeah.
For the moment, we're assuming this is just an empty point in space, because we're not looking at the force acting on a particle here. We're looking for the electric field at this empty location in space.
Oh, okay.
And since electric field is the force on a test charge divided by the charge of that test charge, you could think of this, the electric field vector, you could think of as the force that would be experienced by exactly 1 coulomb of charge. Like if you put a positive 1 coulomb test charge here, the amount of force it experiences is the numerical value of the electric field. But we don't actually have to have a charge there at all. This location in space, even if it's just an empty point in space, this location has an electric field caused by this source charge. So the electric field, I usually think of it as the electric field represents the capability of that point in space to apply a charge to a particle if we put one there. That when we say the electric field here is, let's say, 50 joules per coulomb, or 50 newtons per coulomb. If we say the electric field right here is 50 newtons per coulomb, we're saying if we put a 1 coulomb charge there, it would experience 50 newtons of force. But we don't actually have to have a charge there at all. Saying that this location has an electric field means this location has the capability of applying a force to a charged test particle if we were to put one there. Even if it's just an empty point in space, it could apply a force to a test charge.
I have another question.
Mm-hmm.
If the wall of charges was a negative, then the arrows should be pointing towards it, right? Like what would that look like?
Yeah, so in that case, if these were all negative charges, then for instance, this charge would create electric field pointing towards itself. this charge opposite to it would be creating or electric field towards itself. So we'd have vectors pointing down and to the left, up and to the left. We would still have the up and down components canceling out and the left and left components combining. So we'd still have a horizontal vector. It would just be pointing towards the center of the wall instead of away from the center of the wall.
Got it. Thank you.
And if we were to take a point, Nicole, you mentioned if we're talking about further away or closer to the plate, if we were to take this location and move it further from the plate or closer to the plate, we know at this location we've got, let's say we're really close. If we're really close to the wall here, we've got a vector to the right from the center, fairly large because we're close to it. And then we're still kind of close to these ones, so we get vectors pointing directly outwards, and then further away, directly outwards. But the further away we get, the smaller the contribution is. And when we add these up, we get overall a vector to the right. All the up and down components cancel out. But let's say we look at a location, so if we just add these all together, the summation of all those vectors is just a vector to the right.
Is that what they meant by having the same magnitude? That
Well,
it goes
we're looking at just one location. The idea of the magnitude being the same, let's say we look at a location further out. If we're assuming we're still near the center, like in terms of vertical, if we're still near the center, but we're just further away, outwards to the right, let's say, we're still going to have symmetry. We're still going to have all the up and down components canceling out. But if you look at the individual contributions, let's say the contribution from the center, we're further away. So what would you expect to happen to that contribution?
Less magnitude?
Yeah, it's going to be less magnitude. The contribution from this center charge is going to be weaker as we're further away. In fact, the contributions from all the charges are going to be weaker. But if we're further away, watch what happens to the angle. This charge creates electric field in this direction. This one creates it in this direction. This charge creates electric field in this direction. This one creates it in this direction. This one creates electric field in this direction. This one creates electric field in this direction, and so on. So the individual contributions are weaker, but instead of spreading out a whole bunch, they're now tighter. They're more horizontal and less vertical. And since the horizontal components are combining and the vertical components cancel out anyway, even though these are weaker individually, the fact that they're more horizontal and less vertical means more of it is combining. And it turns out that when you add them up, all these horizontal components add up to, it turns out, the same net electric field as if you were close versus if you were far. Because the part that's canceling out is mostly what's shrinking. The part that's combining is getting larger since the angles are changing. It turns out those effects just nullify each other completely. As you get further away, we expect each individual contribution to get weaker, but also because the angles are becoming more tight, more unified, then we have more of it combining instead of canceling out. So we expect weaker because we are further away, but we also expect stronger because of the more unified angles. And it turns out those effects balance each other out, and it ends up being the same total electric field. So it turns out that if you're close or if you're far, you get the same amount of electric field. However, this is assuming that the plate is infinitely large. That's not realistic, of course. We don't have an infinitely large charged plate. In fact, if there was an infinitely charged plate anywhere in the universe, we would be able to tell from anywhere else because we would have the same amount of electric field everywhere in the entire universe. We don't, so that means there is no such thing as an infinitely large charged plate anywhere in the universe. But we can tell that if you have at least a very large plate, like let's say this plate is not truly infinite in size, it's just very large. So if the plate is large but finite. If you're very close to the center, we can treat it as almost infinite. So we're still going to have electric field pointing straight out. Likewise, if you're on the left side, it would be straight to the left. And if you're close to the center, it's still going to be almost exactly to the horizontal, just straight away from the plate. But as you get further and further out, like let's say you're directly above. At this location, which direction would you expect the electric field to be?
Would it point up?
Yeah, based on the idea that electric field should be pointing outwards from positive charge, we should expect the electric field here to be straight up. And likewise here, straight down. And if we're talking about the other extremes, like let's say we're down in this corner, it's not going to be pointing straight to the right. It should be pointing away from all this charge. In fact, even if you try splitting it up into pairs, we've got some charge below, but a lot more charge above. So the lots more charge above pushes downwards more than the little bit of charge below pushes upwards. So here, the electric field is going to be more down and to the right. And likewise here, down and to the left, away from all this charge. Here, up and to the right, here, up and to the left. And we should expect a smooth transition. Electric field should be continuous. It's going to be something like this. Now, if you ignore the edges, if you're looking at near the center, very close to the center, this looks like a constant horizontal electric field. But as you get further away from the center, it becomes evident that it's not a constant horizontal electric field. You get edge effects when you're further from the center. But as long as this is a very large plate and you're fairly close to the center, you can treat it as almost a constant electric field. The field lines are going to really look more like something like this. Spreading out from this positive source. So again, if you're close to the center and not too far from the plate, you can treat that as almost horizontal, constant electric field. But the further you get from the center, the less true that becomes. Any questions on that so far?
I have a question.
Mm-hmm.
So is the force going to be pointing the opposite direction of the electric field?
That depends on the source particle or the test particle we use. Again, the force is the electric field multiplied by the test charge. So it really depends on what particle we put there. For instance, if you were to put a positive test charge here, the electric field at this location is pointing to the right. If you take a vector pointing in a certain direction and multiply by a positive scalar, what happens to a vector if you multiply by a positive scalar?
It stays the same.
What was that?
Like, it stays the same direction?
Yeah, stays the same direction. It just modifies the magnitude. So the force on this particle is going to be in the direction of the electric field. And note that this matches the idea that a positive charge should be repelled from another positive charge. But we don't even have to rely on the source charge. If we know the direction of the electric field, a positive test charge experiences a force in the same direction as the electric field. On the other hand, if we put a negative test particle here, you take the electric field, which in this case is to the right and a little bit down, multiply that vector by a negative scalar. What happens to a vector if you multiply by a negative scalar?
Switch direction?
Yeah, you get the exact opposite direction. So the force is going to be up and to the left here. And again, that matches the conceptual idea that a negative charge and positive charge should attract each other. But we don't need to worry about the source charge anymore. If we know the electric field, we know a negative test charge experiences a force in the opposite direction, or a positive test charge experiences a force in the same direction as the electric field. But this is really the important relationship there, that the force experienced by the test charge equals the electric field at that location times the test charge itself. But the electric field exists in this region of space, whether you put a test charge there or not. Again, because the electric field represents the capability of this location in space to apply a force to a test particle, whether there's one there or not.
So just to make sure, so for the positive traveling in the same direction as electric field, and then negative as opposite, that's for, so that works for both if it's like a positive source or a negative source, right?
Yeah, although I would caution you, it's not about the direction it's traveling. We don't know anything about which way these are moving. It's about the force that that particle experiences. So regardless of what source is, we don't even, I mean, this is really the advantage of the electric field. Once you know what the direction of the electric field is at that location, you don't even have to care about the source charge anymore. If you know the electric field in this location is, let's say, to the right, that tells you that if you put a positive test charge there, it will experience a force to the right. But if you put a negative test charge there, it would experience a force to the left, opposite to the electric field, because the force is electric field modified by the test charge. So that's a property of the location in space modified by a property of the test particle. And those combined tell you the force that that test particle experiences. So we've got a property of the location in space caused by the source charge. But once we find the electric field, we don't have to care about the source charge anymore. We multiply that by the test charge, and we get a property of the test charge or test object. Any questions on that so far? So if you were to put several different test charges here, different test charges means they're going to experience different amounts of force. But the electric field is the ratio of force felt by the test charge divided by its own charge. So even though differently charged particles experience different amounts of force, the ratio of force over charge is going to be the same. And that ratio is what the electric field is talking about. Again, the capability of applying a charge or a force to a charged object, even if it's just an empty point in space. Any other questions on that so far? So again, if the plate is infinitely large, you'd expect an outwards or inwards if it's negative, but a horizontal electric field perpendicular to the plate itself everywhere and the same value everywhere. If the plate is merely very large, you can treat the electric field as almost uniform if you're fairly close to the center. But the further out from the center you get, the less true that is. But assuming the electric field is constant and perpendicular to the plate is a pretty good approximation as long as you're not too far from the center. And this becomes especially true if we're talking about not just one plate, but a pair of parallel plates. And this is a very common example because it makes a very predictable electric field. If you have two plates, let's say two very large plates, one of them is positively charged and the other is negatively charged. Let's say equal amounts of charge on both, equal size of plates, and they're parallel to each other. If we want to look at the electric field each one of these creates, assuming these are very large, what should we assume about the electric field the positive plate creates, ignoring the negative charge entirely?
It points outwards?
Yeah, it's going to create an electric field outwards in both directions. So if we draw the electric field caused by just the positive plate, that's going to be on the left side, that would be pointing to the left. And we would assume that it is constant. If this plate is large enough, we can assume that the electric field is the same strength, even if we get further away from it. I'm going to call this E plus in the sense that it's the electric field contribution created by the positive plate. And likewise, on the right side, we're going to get electric field to the right everywhere, no matter how far away we are. And again, we're ignoring the negative plate for now. The positive plate creates this constant uniform electric field, staying the same strength even if you get further away. So this is the electric field contribution caused by just the positive plate, ignoring the negative plate entirely. Any questions on that so far? But if we now take a look at the negative plate, ignoring the positive plate entirely, what would the electric field caused by just the negative plate look like?
It'll be going inwards then instead.
So that means on the right side, we're going to get electric field pointing to the left. And no matter how far away we get, it's going to be the same strength. So this would be the electric field contribution caused by just the negative plate. Meanwhile, on the left side, we're going to get charge pointing still towards the negative plate. So that's going to be to the right, because we should expect electric field going towards the negative plate. And again, same strength no matter how far away we get. And remember, we're ignoring the positive plate for the moment. So just electric field pointing towards that negative plate. So that would be again, the electric field contribution caused by just the negative plate. But how would we figure out the total electric field in each of these regions?
Add them up.
We just add up those contributions. In the interior region, we've got electric field to the right, plus more electric field also to the right. So total electric field would be?
To the right.
Yeah, and it's to the right, and it's very strong because we've got these contributions combining completely. So we get net electric field in the interior region is very strong vector to the right. And note that that's from a positive charge towards a negative charge, as we should expect. What about on the right side here? If we add these vectors together, what do we get?
Would it be 0?
Yeah, they're going to cancel out to 0 because we're adding a vector to the right plus a vector to the left. If we assume these are the same amount of charge, we would expect these contributions to be the same because distance from the plate does not matter. If you get further away from a very, very large plate, we would expect the fields to stay the same amount. So these will just cancel out, and we get, in this outer region on the right side, we get no electric field at all. Same thing over here. Electric field to the left plus electric field to the right cancel each other out. So we end up with this very weird situation where in between the plates, we get a very strong electric field, and outside the plates, we get no electric field at all. Any questions on that so far?
Casey, just to clarify, so no matter how far away you are from like the charge plate, you'll have the same strength of the electric field, no matter
as long as it's a truly very, very, very large plate. This is only completely true if the plate is infinite in size, which doesn't actually happen, of course. But as long as the plate is very large compared to the other distances involved, like let's say this plate is maybe like 10 meters by 10 meters, and we're only talking about going a few centimeters away from it, then for all practical purposes, we can treat that plate as almost infinitely large. And so this will be pretty close to true. But if we talk about a smaller plate, like let's say the plate is only a few square centimeters in size and we're going far away from it, then this will not be true.
Okay, so only if it's like a infinite in size plate, then we can get the same strength of electric field no matter like where we go, right? Like no matter how far we go, kind
or
of.
if the plate is large enough compared to the other distances that you can treat it as almost infinite.
Okay, thank you.
And you can kind of see that conceptually based on the idea that if the plate is very, very large, like if you're 1 centimeter away from an infinitely large plate, you look at it and it fills your entire field of vision. It just goes on forever. If you back off to like 10 centimeters away, it's still filling your entire field of vision. So it still acts the same, even if you're a little bit further or a little bit closer, because it's still filling your entire field of vision. If we draw this out as an electric field line diagram, if we know there's no electric field over here, no electric field over here, and in between, we just got this strong electric field pointing straight to the right, that's the same strength everywhere, which we would represent by equally spaced field lines. Our electric field line diagram is going to look something like this. And again, this isn't entirely realistic. It's going to be pretty close to true near the center. But near the edges, we actually get some bending because of the edge effects. For instance, if you take a look at the electric field caused by just the positive plate up here, it's actually going to be up and to the right a little bit. The electric field from the negative plate is going to be down and to the right. So in the exact center, the up and down cancel out, we get just to the right. But if we take a look at, let's say over here, we get contribution mostly up from the positive plate, and then down and to the right, but mostly to the right from the negative plate. Add those up, it's not going to be purely to the right, it's going to be up and to the right. So what we actually get near the top is more going outwards and then bending back towards the negative. Outwards a little bit and then bending back towards the negative. Up here it's going almost straight up, but then bends back towards the negative, just like in a dipole. And likewise down here. Near the edges, it's going to be bending. In fact, even out here, it's going to be bending outwards, bending around the bottom, coming back in like this. So very much like a dipole, but more sort of stretched out. And in fact, you would actually get a little bit of electric field in the outer regions. It's going to be very weak because it mostly cancels out, but the electric field is going to look something more like this. Very weak, which you can see by these field lines being more spaced out. Very strong in between the plates. So as an approximation, you can treat the electric field as very strong and almost constant in the in-between regions, very weak and almost zero in the outer regions. If you're near the edges, that kind of breaks down, but as long as you're near the center, it's very close to valid. And this is a very convenient way of setting up an electrical experiment. If you want to perform an experiment in a constant electric field, all you really need to do is create a test chamber where the walls, you've got parallel walls that are positively charged and negatively charged, and you can guarantee that in the in-between region, the electric field is relatively constant and very predictable. Like, how would you change the strength? Let's say this electric field is not strong enough and your experiment needs a stronger electric field. How could you modify that?
Increase the voltage?
What do you mean by voltage here? How would you actually do that in terms of what's going on with these plates?
Oh, actually, maybe bring them closer to each other.
If you put them closer or further, would that actually matter? Maybe. I think if you, I don't think that would actually make a difference in this case. If we just move these plates closer, then this plate is still creating the same electric fields as it was before, and so is this one. So let's look at the same electric field in between. But what are the only properties of these plates that really influences how much electric field they're going to be creating? If distance doesn't matter, what's the only other thing that does?
Size, like make it longer?
Well, we're assuming they're already infinite in size. So the size doesn't really influence it here.
Is it the charge?
Yeah, the amount of charge. Or really the density of charge, because we're already assuming these plates are so big they're practically infinite. But how tightly packed the charge is matters. So if you want a stronger electric field, you just put more charge on each of these plates, and that increases the strength of the electric field in between. Also, if we take a look at voltage, let's assume that these plates are large enough that we can assume that we can treat it as constant electric field in between and no electric field on the outside. We've just created this chamber where we've got these plates of parallel charge plates. In between, we've got a constant strength electric field. And outside, we've got no electric field at all. We can also use this with the idea of voltage, because voltage is related to electric field in the same way that potential energy is related to force. Electric field is the negative derivative of voltage. Or since the electric field is constant, we can just treat this as the rate of change in voltage over change in position, which means that change in voltage is negative electric field times distance. We've got a constant electric field, so that means the voltage is changing at a constant rate. You go forward 1 centimeter, you get a certain amount of change in voltage. That ratio of how much the voltage changes per centimeter is the amount of electric field. So let's say we start at, first of all, the electric field should be pointing from what voltage to what voltage?
High to low?
Yeah. So that means if the electric field is pointing to the right, we can expect the left side to be high voltage zone. And the right side, the point that it's pointing towards, to be a low voltage zone. And if we draw in the equipotential lines, we should expect those to be perpendicular to the electric field. So that's going to be something like this, 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 this. These would be the equipotential lines. Maybe you're going from like positive 10 volts to 5 volts to 0 volts to negative 5 volts to negative 10 volts. And those should be equally spaced because the difference in voltage and the difference in distance are proportional to each other because the electric field is constant. Constant electric field means you get the same change in voltage per centimeter. So if this distance represents, let's say, losing 5 volts, the same distance further forward would also represent losing 5 volts, then losing another 5 volts, and so on. So the fact that we've got this electric field in between these plates creates a difference in voltage. So you could say that these plates are at different voltages because there's an electric field in between them. And where have you seen this before? Where in 7b were we dealing with parallel plates that have a difference in voltage between them? Because there's charge stored on them.
Conductors?
Hmm?
Was it conductors?
Well, the plates themselves are conductors because we're allowed to move charge onto them and off of them. But what if we attach these to some wires and then attached a battery and a resistor and a switch?
Capacitor?
Yeah, this is a capacitor. This is exactly the capacitor we were looking at in 7b. It has a difference in voltage, high voltage and low voltage, because it has accumulated some charge on these parallel plates. But this is what's going on inside the capacitor. Once you attach charge to the plates, those charges create electric field. That electric field is associated with the difference in voltage. Electric field points from the high voltage zone towards the low voltage zone. That difference in voltage is the delta V capacitor that we were looking at in 7b. The more charge it accumulates on the plates, the more difference in voltage you get. But this is what's going on inside the capacitor. The charge on the plates creates an electric field in between the plates, but no electric field on the outside. It all cancels out. So this doesn't interfere with everything else. Instead, you just get this strong, constant electric field in between the plates, depending on the amount of charge. That electric field is associated with a change in voltage, and that's the delta V capacitor we've been looking at from the outside in 7b. This is now what's going on the inside of the capacitor. This is the reason why it works. Any other questions on that? All right, take a look over that chart of these important quantities, voltage, electric field, force, potential energy on mathandcheese.org. Make sure you understand what each of those means, how they're related, how to convert from one to the other. And feel free to email me if you want to go over any specific examples next time. You're welcome. See you later.